everyone, and welcome. You know that feeling when you're staring at a chemistry exam and your brain just starts to bubble over with confusion? Well, you are definitely in the right place. Today, we are going to break down some of those core laws about solutions, the kind of stuff that shows up everywhere, in real life and, yep, on your tests. Let's dive in. It kind of sounds like the setup for a really weird joke, right? But the answer, of course, is chemistry. Specifically, it's these really cool, predictable laws that explain how different things mix and interact with each other. And these aren't just ideas in a textbook. They explain the world all around us in some pretty fascinating ways. So here's our game plan for today. We're going to start with the laws of pressure in vapor. Then we'll get into properties that are all about just counting particles. And we'll wrap up with a little plot twist that kind of changes all the math. So let's get going with our first law. First up is Henry's Law. This is the science behind that super satisfying shh sound you hear when you crack open a can of soda. It's all about how gases act when you dissolve them in liquids. So what does that actually mean in plain English? It's pretty simple. The more pressure you put on a gas that's sitting on top of a liquid, the more of that gas is going to dissolve into the liquid. Just picture it. You're literally pushing the gas molecules down into the gaps between the liquid molecules. And of course, there's a nice, simple formula for this. Here, P is just the partial pressure of the gas, X is its mole fraction, which is basically just a way of saying how much of it is dissolved, and KH is what we call Henry's constant. It's a unique number for every gas and liquid combo. Okay, if you need to remember one thing about Henry's Law for an exam, this is it. Seriously, burn this phrase into your brain. If the pressure goes up, more gas dissolves. If the pressure goes down, like when you pop that soda can, the gas becomes less soluble and it escapes as all those tiny bubbles. And this law is a huge deal, way beyond just soda cans. It's why scuba divers have to come up to the surface slowly to stop nitrogen from bubbling out of their blood too fast. And it's also why mountain climbers can struggle to get enough oxygen at high altitudes. There's just less atmospheric pressure up there to push the oxygen into their lungs. All right, next up, we're going to shift gears from dissolving a gas in a liquid to mixing two liquids together. And this brings us to Raoult's law, which is all about something called vapor pressure. So, this law is all about how easily a liquid wants to escape and turn into a gas. That's its vapor pressure. And it says that for a perfect, or what chemists call an ideal solution, the vapor pressure of each liquid in the mix is just a fraction of what it would be if it were all by itself. And that fraction, it's simply its mole fraction, how much of it you've got in the mix. And here's the formula. PA is the vapor pressure of your first liquid, A, once it's in the mixture. XA, it's its mole fraction. And that PA0 with the little circle, that just stands for the vapor pressure of liquid A when it's totally pure. So it makes sense, right? The more you dilute it, the less it contributes to the total vapor pressure. But what exactly is this ideal solution? Well, you can think of it like a perfect friendship. The molecules of liquid A are just as happy hanging out with molecules of liquid B as they are with their own kind. When you mix them, there's no big energy change and the final volume is exactly what you'd add up. Benzene and toluene are the classic textbook example of this. But let's be real, most solutions aren't perfect. If the molecules in the mix don't really like each other that much, meaning they have weaker interactions, they're going to escape more easily. We call that a positive deviation, and it gives you a higher vapor pressure. But if they're super attracted to each other, they hold on really tight, which leads to a negative deviation and a lower vapor pressure. Okay, let's completely switch gears. We've been talking about what the particles are. Now, we're going to talk about just how many particles there are. So welcome to the world of colligative properties. This is it. This is the absolute key concept for this whole section. For these specific properties, it doesn't matter one bit if you dissolve sugar or salt or some other crazy chemical. All that matters is the sheer number of individual particles you dump into the liquid. It is purely a numbers game. And for your exams, and just for understanding how things work, there are 4, and only 4, key colligative properties you really need to know. And here they are. When you add stuff to a liquid, you lower its vapor pressure, you raise its boiling point, and you lower its freezing point. That last one, that's why we salt icy roads. The salt particles get in the way and make it harder for water to form ice, so it has to get even colder to freeze. And finally, you have osmotic pressure, which is absolutely critical in biology. So it's all about just counting particles, right? Sounds simple. Well, almost. There's a plot twist, and it's called the Van't Hoff factor, or just I for short. This is the million-dollar question. What happens when you dissolve something like table salt, NaCl, and it breaks apart into two separate ions, a sodium ion and a chloride ion? All of a sudden, the one particle you thought you added is now two. Or what if molecules decide to team up and stick together? Our simple particle count is suddenly totally wrong. And that's exactly what the I factor is for. It's our correction factor. It's the little number we use to fix our math to account for what the particles are actually doing once they're dissolved. It tells us how many effective particles are floating around for every single one we thought we put in. Let's look at a few quick examples to make it super clear. For something like glucose, which just dissolves without breaking apart, I is exactly 1. For NaCl, which splits into two ions, I is going to be greater than 1. And for something like acetic acid, which can actually pair up in some solvents, I ends up being less than 1 because you have fewer effective particles than you started with. Okay, so let's do a super quick recap of those two big laws we started with. Henry's law? That's for a gas in a liquid, and it's all about pressure. Raoult's law? That's for a liquid in a liquid, and it's all about the mole fraction. Just knowing that basic difference is going to help you a ton. So after all that, what's the big idea? From how we make ice cream to how the cells in our own bodies stay alive, the world is shaped in these profound ways, not just by what kinds of particles are in a solution, but often just by how many there are. It's a pretty powerful reminder that in chemistry, sometimes quantity has a quality all its own. Thanks so much for tuning in.